Hello and welcome. Today, we're going to explore a frontier in chemical synthesis, one that promises to dramatically accelerate the discovery and production of new materials. We'll be taking a deep dive into a paper by Bobby Sumter and colleagues at Oak Ridge National Laboratory and the University of Tennessee, titled Autonomous Continuous Flow Reactor Synthesis for Scalable Atom Precision. Our modern society increasingly relies on science to solve grand challenges, from global health crises like the COVID-19 pandemic to long-term goals in energy and sustainability. The recent pandemic in particular highlighted the critical need to rapidly deploy science to solve complex problems on an unprecedented timeline. This puts pressure on our traditional scientific approach, often described as make, measure, model. This linear process is excellent for incremental discovery, but it can take many years and substantial investment to deliver scalable solutions. To meet today's challenges, we need something faster, something more efficient. The authors of this paper argue that we are at a point of confluence where three key capabilities are coming together to create a new paradigm. First, we have leadership-class computing with exaflop speeds that allow for computational experiments of extraordinary scale and integrity. Second, we have data-accelerated approaches like artificial intelligence and machine learning that can analyze and infer critical information from data at the speed of the experiment itself. And third, we have advanced synthesis and material science. The key is to integrate these capabilities. Right now, developments in these areas often accelerate only one part of the scientific process. The real potential lies in creating a unified autonomous system. This is especially critical in the field of chemical synthesis. Synthesis provides the foundation for countless technologies, from solar energy and battery storage to catalysis and quantum materials. To meet the evolving demands of science, we need the ability to perform scalable chemical synthesis with atomic-level precision. This is an immense challenge due to the incredibly high dimensionality of chemical and reaction space, the near infinite number of ways molecules can be combined and reacted. This is where the idea of an autonomous approach becomes so powerful. Imagine a system that uses artificial intelligence to guide its own research, analyzing data as it's produced to create and test new hypotheses in real time. This could expedite the pace of scientific discovery by orders of magnitude. The authors propose to achieve this using a framework known as continuous flow chemistry.
So, what is flow chemistry? Unlike traditional batch chemistry, where reactants are mixed together in a flask and left to react, flow chemistry involves continuously pumping reactants through a network of tubes or channels. This might seem like a simple change, but it offers profound advantages. Because the reactions happen in small, well-defined channels, we have unprecedented control over conditions like mixing, temperature, and pressure. This leads to better reproducibility, higher yields, and enhanced safety, especially when dealing with hazardous reactions. It also allows for real-time monitoring and makes it much easier to scale production up from the lab bench to industrial quantities. For polymer synthesis, this approach can overcome challenges like poor control over reaction processes and the difficulty of producing large quantities of high molecular weight polymers. The authors are building on a rich history of progress in this area. Over the last 2 decades, researchers have been steadily moving towards more intelligent and automated flow systems. Early work, for instance, demonstrated the use of microfabricated reactors with inline detectors to monitor photochemical reactions as they happened. More recently, the focus has shifted to using algorithms and automation to actively explore chemical space. Some platforms have integrated high-performance liquid chromatography and mass spectrometry directly into the flow system, allowing for the real-time analysis of thousands of reactions per day.
This automation opens the door for machine learning. The earliest self-optimizing flow reactors used algorithms to guide reaction optimization. Now, more sophisticated AI strategies are being employed. One of the most fascinating areas is in retrosynthesis, which is the process of working backward from a desired target molecule to figure out the simplest, most effective starting materials and reaction steps. Researchers have developed neural networks that can predict these synthesis routes by learning from vast databases of known chemical reactions. One approach used a similarity-based method, where the algorithm finds known reactions with similar products and reactants to predict the forward strategy, essentially mimicking a chemist's intuition but on a massive scale. These AI-driven planning tools are now being integrated with physical hardware. Researchers at MIT, for example, developed an open-source software framework called ASCOS that combines an AI retrosynthesis algorithm with a robotically reconfigurable flow apparatus. This system can automatically build itself into the right configuration to perform a reaction, optimize the conditions, and enhance the yield, all while receiving constant feedback from online analytics.
The complexity of these systems continues to grow. We've seen the development of radial synthesizers that can run multiple reactions in parallel, using a central switching station to expose chemicals to different conditions. We've seen the use of machine learning models, like random forests, to predict the yield of complex cross-coupling reactions with high accuracy. And we've seen deep reinforcement learning, the same type of AI used to master complex games, being used to optimize chemical reactions faster and more efficiently than any previous method. This has culminated in the concept of the self-driving lab, or the robotic chemist. Scientists at the University of Liverpool, for instance, programmed a mobile robot with a Bayesian optimization algorithm to search for highly active photocatalysts. Over 8 days, the robot autonomously performed 688 experiments and discovered a mixture that was 6 times more active than the starting point, a task that would have taken a team of humans several months. This is the state-of-the-art that our authors are building upon. They note that while tremendous progress has been made, there are still hurdles to overcome to achieve a truly autonomous flow chemistry platform, especially one that can handle complex multi-step syntheses. The ultimate goal, as one recent review put it, is to have a continuous flow platform that can design its viable pathway to a particular molecule and then carry it out on its own. And this is precisely the system that Sumter and his colleagues are developing. Their approach is a comprehensive, 4-part vision for an autonomous reactor that can translate promising lab-scale molecules into scalable quantities with atom precision.
The first step is the physical hardware. They envision a continuous, reconfigurable, and robust flow system designed for multi-step chemical synthesis. A critical part of this is building in a suite of inline characterization tools. This means the analysis happens automatically as the product flows out of the reactor. The techniques they are integrating are extensive: NMR for molecular structure, infrared and Raman spectroscopy for vibrational modes, GCMS and HPLC for separation and identification of compounds, and even ex-situ methods like X-ray and neutron scattering for more detailed structural analysis. This multimodal analysis provides a rich, real-time picture of the reaction's progress. The second step is the interface, linking the sophisticated hardware to intelligent software. This involves developing systems for remote operation, control, and data storage. They plan to use specialized flow cells that allow reactions to be modulated by external fields, like electric or magnetic fields, or stimulated by light. This requires new algorithms and processing workflows to handle the data from all the different analytical tools, and, crucially, to create a feedback loop that can tune the reaction parameters on the fly. The third step is the core software stack, the brain of the operation. This is where artificial intelligence takes center stage. The system will use deep learning and reinforcement learning alongside traditional physics-based models like quantum chemistry and molecular dynamics to drive the synthesis. Pre-training these AI models on existing chemical data is key to making them efficient enough to work in a real-world lab. Finally, the fourth step is the computational backend. An autonomous lab will generate a torrent of data and require a wide range of computational tasks, from real-time analysis to complex simulations. The system needs to be intelligent enough to parse these tasks to the appropriate computing resources, whether that's a small, lightweight computer at the edge, a mid-level GPU server, or a leadership-class supercomputer for the most demanding calculations. This requires a decision-making framework to manage the computational workflow efficiently.
So this is the vision, but how does it perform in practice? The authors provide 3 preliminary examples to highlight the potential of this approach for tackling difficult chemical challenges. First, let's look at selective deuteration. Deuterium is a stable isotope of hydrogen, and replacing hydrogen with deuterium in a molecule can be incredibly useful. It can reveal a lot about reaction mechanisms through what's called the kinetic isotope effect, and it's essential for certain analytical techniques like neutron scattering, which can probe the structure and dynamics of polymers. The target molecule here is metatoluidine. The traditional method for deuterating this molecule is a batch synthesis using a parse reactor. This requires harsh conditions, a temperature of 180 degrees Celsius, and is very inefficient, needing a large excess of the deuterium source and catalyst. The result is a tedious workup process and limited scalability. In contrast, using a continuous flow reactor equipped with an embedded catalyst, the authors achieved selective deuteration with much higher efficiency. The schematic shows how reactants are pumped into the system, pass through the catalyst, and emerge as the deuterated product, with inline analysis providing feedback. Looking at the data in their table, the flow synthesis ran at a lower temperature, took only about 12 minutes compared to over 40 hours for the batch method, and produced a higher yield of 96% versus 80%. More importantly, the authors note their flow process is scalable, capable of producing about 4.8 grams per hour. This is a clear demonstration of how flow synthesis can make a difficult, inefficient process both robust and scalable. The second example is cross-coupling reactions. These reactions, which form new carbon-carbon bonds, are a cornerstone of modern organic synthesis. The authors targeted the synthesis of a specific molecule, 2,5-dibromo-1,1 biphenyl, which is a precursor for making materials like graphene nanoribbons. Scheme 2. Using traditional batch methods, the yield for this reaction was low, less than 30%. The authors attribute this to the limited stability of the reaction intermediates and steric hindrance. When they switched to a flow reactor, the yield improved dramatically. The table shows that in just 5 minutes of reaction time in the flow system, they achieved a yield of around 72%, which increased to 83% after 20 minutes. The batch reaction, by comparison, only reached a 28% yield after a full hour. The author suggests this success is due to the efficient mass transfer in the flow reactor, which is better at handling reactive or unstable intermediates that would be problematic in a batch flask. This also highlights a key point. The parameters in a flow system are much easier to tune, which makes it a perfect platform for AI and machine learning-driven optimization. The final, and perhaps most complex, is polymerization. The authors focus on copolymers, which are polymers made from 2 or more different types of monomers. The way these monomers are arranged along the polymer chain, whether they are in random order, in alternating blocks, or in a smooth gradient, dramatically affects the material's properties. We can see a schematic representation of these different arrangements. Synthesizing these structures with precision is a major challenge in polymer science. The authors set out to create gradient copolymers of styrene and butyl acrylate, which are commercially important for paints and coatings. A gradient copolymer exhibits a gradual change in composition along the chain. This structure gives them unique properties, like broad glass transition ranges, that are different from block or random copolymers. Typically, making these requires complex, slow, controlled polymerization methods. Here, the authors demonstrate the synthesis using a simple flow polymerization setup. They show a schematic where styrene and butyl acrylate are pumped through a micromixer and into a heated reaction coil. The results are remarkable. The NMR spectra confirm the successful synthesis of the copolymer. The bottom spectrum shows the result from a traditional batch reaction, which took 24 hours. The top spectrum shows the result from the flow reactor polymerization, which achieved a similar composition but with a retention time of only about 25 minutes. This is a massive acceleration. The authors note that by simply tuning pump speeds and temperatures, they can create copolymers with different compositions. This is where the true power of an autonomous system lies. By integrating inline NMR analysis, the system could monitor the reaction in real time, get feedback on the polymer structure being formed, and adjust the flow parameters to precisely control the final architecture. So, to summarize, the authors have reviewed the state-of-the-art in automated synthesis and outlined a comprehensive vision for a truly autonomous discovery platform. This is a data-driven ecosystem that moves beyond the linear make, measure, model process. It uses interconnected instruments and AI-driven feedback loops to accelerate precision synthesis and materials discovery. The advantages are clear. It opens up the possibility of discovering new kinetic and thermodynamic reaction pathways. It allows for the production of target compounds much faster and more efficiently, with optimal synthesis protocols stored as digital recipes. It enhances safety by controlling sensitive reactions, and its modular nature means it can be deployed rapidly where needed. To place their work in context, the authors performed a literature analysis on the topic of continuous flow synthesis. They found over 7,000 publications, with a dramatic increase in recent years, indicating a surge of interest in this field. A keyword map shows that research is focused on areas like efficient, multi-step organic synthesis with an emphasis on optimization and scaling.
But they also found something else. Of all these publications, only a small fraction, less than 3%, were focused on polymer science. This highlights that their work is not just an incremental improvement, but a targeted effort to bring the full power of autonomous, data-driven synthesis to the complex and high-impact field of polymer materials. Their work establishes a clear indication of the utility of a real-time, data-driven approach to continuous flow synthesis, accelerating the pace of discovery for polymers and other advanced materials.